Hello, everyone. I'm Kai, and to everyone online and here, welcome to this talk titled Algorithmic Decision Making and Participation for Biodiversity Conservation. I am particularly delighted to have Dr. Lily Xu with us today to discuss technical advances in machine learning, optimization, and causal inference that are designed to improve resource allocation for conservation management. Lily is a computer scientist developing methods across machine learning, optimization, and causal inference for environmental management. She aims to enable practitioners to make effective decisions in the face of limited data, taking actions that are robust to uncertainty, effective at scale, and future-looking. She's currently a postdoctoral researcher fellow with the Leverhulme Centre for Nature Recovery at Oxford, which is why we're lucky to have her. And soon she will begin as an assistant professor at Columbia University, when we'll have to go all the way to New York to listen to them. She's also—
You're all welcome.
She also serves as the AI lead for the SMART partnership. Just so everybody is aware, this event is being recorded and will be posted on the website. So anything you say will get recorded. Q&A from the room can be interspersed with the talk. For online questions, we'll hold them off till the end. Yeah, that's it. Thanks. Take it away.
Thank you so much, Kai, for the invitation and that introduction. And it's just very fun to be here with all of you. And I'm very happy to keep this interactive, so please feel free to interrupt at any point. But I'll motivate my work with the biodiversity crisis, which some of you may or maybe have varying levels of familiarity with. But just some stats. So in the past 50 years, we've seen an average decline of 70% in the average size of vertebrate populations. And the UN has estimated that there is currently 1 million species in danger of extinction within our lifetimes. And this is out of only about 8 million species on this planet. So it's a very large-scale, urgent challenge. And part of the reason why biodiversity matters is because aside from just the intrinsic value of plants and animals, they also provide a host of ecosystem services that benefit us all. So, for example, the climate crisis and the biodiversity crisis are very much intertwined, where nature-based solutions can contribute up to 37% of the necessary CO2 reductions necessary to halt climate change and keep to the Paris Agreement. Biodiversity is very closely tied with our own health and well-being. So this fantastic paper from AER last year showed a causal relationship between the decline of a single species, vultures, in India, which caused human mortality to increase by 4%. So this is a very measurable impact of the loss of a single keystone species. And the really important thing about this paper is that the vulture decline happened in 1993, and then this paper didn't even come out until 30 years later. So it just, kind of a warning to us about the potential hubris of not being aware of these challenges and the value of ecosystems before it's too late. And importantly, biodiversity is also very closely linked to food insecurity and global development, as the availability of wild bushmeat and fish are a critical protein source for many of the world's poorest people. So there is increasing attention internationally to the importance of biodiversity. So in 2022, biodiversity really had its Paris Agreement moment, where 196 nations around the world signed the Global Biodiversity Framework, which is a list of about 30 agreements. And one of the most important is an initiative known as 30 by 30, which is a commitment to increase the amount of the world's protected land and water to 30% by the year 2030. So this involves almost a doubling of the world's protected land and over tripling of the world's protected oceans. But one of the biggest threats to biodiversity, especially within protected areas, is rampant poaching, where poachers will come into animal habitats, including in protected areas, and place traps to catch animals. So this is a Guardian article from 2023 of Murchison Falls National Park in Uganda, which is a site that I've had the privilege of working with for over 6 years. And this is a team of rangers in front of this mountain of snares that were confiscated from a single year within the park. So every single one of these small wire circles corresponds with one animal life that could have been caught. And these big metal traps at the bottom are claw traps meant to ensnare elephants, buffalo, and other big game. So the poaching crisis is so rampant that some people refer to the fact that even inside protected areas, these parks are sometimes no more than paper parks, where there are lines drawn on a map, but there's not actually effective conservation within them. And ecologists have estimated that in Murchison Falls, there's about 4 snares for every square kilometer in the park. And this is a massive 5,000 square kilometer park, so that's about 20,000 snares. But there's unfortunately only 250 rangers available to conduct patrols and find and remove as many of these snares as possible. So it's a huge challenge of limited resources. And to just get a better sense of why this problem is so difficult, here are 3 pictures of snares in Murchison Falls. And even though these are head-on photos, you can see how difficult it is to find. So I've circled here where all the snares are. This is to understand the challenge of patrolling a large forest, trying to look for these snares. So the data that we have comes from ranger patrols. So when rangers go on the patrols, they'll carry GPS trackers to record where they've been and where they found signs of poaching and other activity. So this is a map of Murchison Falls, and every single little brown circle corresponds with a GPS waypoint of where they've been. And you can see by looking at this map that it's fairly unevenly covered. So there's many areas in green that rangers haven't been to a single time, even across over 6 years. And then you can see that there are other areas that are patrolled much more intensely. So the question is, are there important poaching hotspots that we're missing out on that rangers just haven't spent enough time at? And on top of just the GPS locations, we also have patrol observations located in some of these coordinates. So they might be tagged with biodiversity signs or signs of poaching, such as indications of a snare or ashes from a poacher's campsite. So the way that we start to process this data is we take the park and we discretize it into 1 by 1 square kilometer regions. So every single pixel here corresponds with a 1 square kilometer grid cell. And we also temporally discretize time into 1-month intervals. So the way I'm measuring historical patrol effort is look at each cell for each month in the historical time period and seeing how far did rangers patrol in terms of distance walked in kilometers. So we can kind of we can string together all of these GPS trajectories and use that to measure the amount of coverage in each cell. And we also have for each area whether or not they observed snares. So this is a heat map that shows that a lot of the snare activity, for example, has been found in the northwest corner close to the water source. And we also, especially for the data scientists here, we also have a wide variety of geospatial features that we add that we believe might be correlated with poaching threat. So we have information about human features, such as how far we are to the nearest road, park boundary, or patrol post. We have landscape features, such as how far we are to the nearest water hole, the elevation, the ruggedness, how difficult it is to traverse an area, and land cover. And we also have a number of dynamic information that changes over time, which comes from remote sensing. So all of this data comes together into supervised learning models that we build to try to predict poaching threat in the future based on our past observations. And really the goal is to try to predict poaching risk for different months over time, because there are a lot of differences with seasonal patterns, for example, and also to focus on predictions on areas that have been infrequently or not patrolled in the past. And I won't go into details, but the way that we built this model builds a specific ensemble that's meant to overcome strong class imbalance, which we have in this problem setting. But after we evaluated the performance of our model, we wanted to know how well it did, not just in terms of AUC, but also in performance on the ground. So we implemented a 5-month field test in Murchison Falls, where we took the areas that we had predicted to be at high risk, selected a random subset of those, and then selected a random subset of medium and low risk areas, and asked rangers to patrol those areas for a fixed period of 5 months. And to keep it a valid experiment, we focused on areas that were infrequently patrolled in the past. And we also kept it a blind experiment by not informing them of the risk classifications in advance. So later on, they shared their data with us. And what we found is that they observed many more snares in the areas that we predicted to be at high risk of poaching than medium or low risk. And then in another month, when we were focused on high risk areas, we had a team find over 1,000 snares in a single month, which compares to a typical month where they find between 300 to 500 snares. So we were excited about that improvement, but we were even more excited to get really positive feedback from our partners. So Rohit Singh leads the Zero Poaching Initiative at WWF and said, "I'm super excited with the results, and let's get this going on other countries too." So that's something that I spent a large part of my PhD focused on, thinking about how to effectively scale this approach up. So this is in partnership with SMART, which is the spatial monitoring and reporting tool, which develops the phone app and accompanying desktop software used for protected area managers. And SMART is comprised of a group of 8 different conservation NGOs. And this platform is widely adopted in many parks, but it's mostly just a database system, and at that time had no ability to prescribe or make recommendations. So what we did was integrate our machine learning predictions as a plugin into this platform so that this tool will be available to park managers, kind of meeting them where they are, so they don't have to do any additional data collection or adopt with like any new platforms. It's really taking the data that they're already storing and helping them find better ways to leverage it. And SMART is widely used by over 1,200 protected areas worldwide, so that makes our system also available to them as well. But there's several parks on the platform, which are like Murchison Falls, which have a lot of historical data. But there's other parks which are just starting to begin using effective data collection. So I had spoken with Leverhulme State Park in Malaysia, who are really interested in the work that we had done in Uganda and also Cambodia. And said, we would really like help with our patrol planning as well. Can you help us make predictions? I said, we'd be happy to. They sent their data over, and this is what we found, which was only about 3 months of data. Less than half the park had been patrolled at all. And this is just simply not enough information to inform a machine learning model. But what that did tell us was what we should focus on next in terms of a research direction, recognizing that when we have data-rich settings, we can leverage that historical data to build effective models for planning. But in other contexts where we're really data scarce, like for Leverhulme State Park, we have to think about how to conduct patrols to simultaneously detect poaching activity, while also making sure that we're exploring areas with high uncertainty so that we can do better in the future. Some of you might recognize this trade-off as emblematic of the exploration-exploitation trade-off, which is foundational to online learning, which is a branch of machine learning in which we have to kind of take action like in a real-world setting, and our actions enable us to both like collect potential reward in the present time, with the opportunity of also being penalized if our actions are suboptimal, and then immediately feed that new data back into our model so that we can update our model in the future. And I won't go into the details of our algorithm, but basically we design a new version of an online learning algorithm for this setting, using the framework of multi-armed bandits, which is kind of the classic paradigm, where each arm of a multi-armed bandit corresponds with a different action that we can be taking. So here, one arm corresponds with patrolling one area in the park, for example. And we leverage problem-specific structure that we have in this context. So specifically, the reward, which is our cumulative expected probability of finding snares, has the following characteristics. So this reward structure is decomposable because the total reward of combinatorial patrol is the additive sum of our reward for visiting each unit. So that brings us into the world of combinatorial bandits, where we can really leverage this decomposable action structure. We have Lipschitz continuity, so that there's similarity across different areas of the park that have similar features. So we can kind of embed all these arms in some metric space and leverage the similarity across features. And we also have monotonicity in our reward function, where we're looking at the amount of patrol effort that we can exert in a single month. So let's say that in total, rangers have 40 hours that they can spend, and we want to allocate these 40 hours across some subset of regions. So the question of should we spend 30 minutes in this area or should we spend 3 hours in this area is one of the key trade-offs that we have to consider. And what we leverage is the fact that when we spend more effort in one area of the park, we're never going to be less likely to find a snare. So our expected probability of detection is monotonically non-decreasing, but with diminishing returns. So we have to kind of capture that. But basically, by bringing together all these problem features that we can represent mathematically, we're able to also contribute new theoretical results for multi-armed bandits, where by comparing to previous results in Lipschitz bandits alone that looked at smoothness but not decomposable reward structure, we're able to improve upon the existing regret bound for Lipschitz bandits alone to do better in terms of our expected loss compared to the optimal action that we could be taking. So basically, by incorporating the mathematical structure embedded in our problem setting, we're able to reduce the amount of unnecessary exploration we have to do so that we can converge faster in a shorter time horizon to an optimal action. So I just wanted to showcase that as like a sample of how this type of work and use-inspired machine learning can really create a lot of benefit in terms of surfacing new interesting research directions that can then translate into more generalizable problems. But then like a follow-on question that you might want to ask is recognizing that the assumptions I've been making so far have been one of stochasticity. So there's noise in this problem setting. So, on a given month, when we visit an area, there might be poaching, there might not be poaching, but with some kind of expected overall expected level of poaching. So maybe over in expectation, there's a 70% chance of finding snares or 20% in one region, and every month it's going to be a little stochastic. But aside from just kind of the noise inherent in this problem setting, you can also imagine another component that makes the problem more dynamic, which is that we're working kind of against strategic agents who are humans who might be smart and realize that my snares are being taken away. Maybe I shouldn't keep going here and I want to go somewhere else in the future. So, a very natural question might be like, how are poachers respond to our patrols, and can we model their response so that we can do better planning? So this took us on like a years-long journey where we're trying to answer a question that sounds very, very simple, which is, do ranger patrols deter poachers in the future? This assumption of deterrence is actually one of the foundational assumptions in the SMART approach for protected area management, because some ecologists have done studies where they place fake snares and ask rangers to collect them, and they found that rangers only find about 10% of the snares that they put out, even in areas that they do patrol. So some naysayers, even those who are like very passionate about conservation, say that snare removal is too hard a challenge. If we remove 100 snares, 100 more will be placed tomorrow. There's like no point in even trying. We should focus our efforts and money on something else. But then there's other people who are very passionate about this who say, no, like ranger patrols are the only mechanism that we really have. And aside from the direct impact of physically removing a snare, there's also the indirect impact of discouraging them from coming back in the future. But those kinds of arguments, have never really had conclusive evidence on either side. So we tried to see if we can more rigorously address this question. But for anyone who's worked on causal inference in settings such as this, you'll recognize how difficult this problem setting is, because the gold standard for causal inference is to conduct an RCT, but that's simply not possible in this setting because it costs a lot of money. But more importantly, the opportunity cost is too high. So if we randomly select some areas to be a controlled site and we say, don't patrol here for a few months, if those end up being like poaching hotspots, rangers would not, park managers would never feel comfortable doing that. So what we have to do instead is we have to somehow find a way to leverage existing observational data for such a study. In fact, what we leverage in this paper is the field test that we conducted back in 2018, where we picked a random selection of high, medium, and low risk areas for rangers to patrol. That actually served as a shock to the system, where we changed ranger behavior for the course of a very controlled 5-month period of time, because we were focused on patrolling infrequently patrolled areas. So that 5-month period created a shock that introduced quasi-experimental variation in the setting, which let us set up causal analysis. And the second key challenge that we had to overcome in this setting is imperfect observation of the outcome variable. So we've seen how difficult it is to find snares. And I also want to point out that because this park is very big, the amount of coverage that rangers are able to do in a given month is quite low. So in a single month, rangers are only able to patrol about 8% of the cells in a park. So that means 92% of the sites every month, we have no idea what's happening. But even in those 8% of sites that we can patrol, there's imperfect observation. So if we patrol an area and we find a snare, then that's a true positive label. So we can be very confident that there is poaching. But if we don't observe a snare, there's uncertainty as to what that true outcome could be. So trying to disentangle the detection of snaring versus the true presence of snaring is a key challenge. And the way we overcome this challenge is by building a Bayesian inference model combined with machine learning predictions of general poaching probability to impute missing outcomes. And the key assumption here is really leveraging that same intuition that I described earlier, where for any negative label that we have, if rangers only patrolled very quickly, like they just walked 15 minutes through a site, then if they didn't find anything, we have no idea what really happened. But instead, if in a single month they patrolled very intensely and they were there for 5 hours, we can be much more confident that's a true negative label. So we're using patrol effort as a proxy for the reliability of each negative label, and we use that we use patrol effort to do this imputation. I want to highlight here the way the place machine learning comes into this causal inference process. So as I mentioned, this park is very large and rangers are only able to patrol on average 8% of the park in a given month. But every month looks very different. So these are 2 consecutive months, January and February. And you can see, indeed, the coverage is very low, but also that it changes drastically from month to month. So it's like a highly stochastic setting. It's very, very noisy in terms of where we're able to get observations. So we wanted to see, for example, how are patrol patterns different this month compared to typical levels. There's not a good sense of what we can use as typical levels of patrolling, because we can't look at last month, we can't look at last year. So instead, we have to find some notion of typical patrol effort so that we can use that as our business as usual baseline to evaluate our treatment effect. And the second challenge is that, in part because our coverage is so sparse, therefore our poaching outcomes observations are also extremely sparse. So the amount of detections we're able to make is very low. So this is where we bring in machine learning to take this very, very messy, so very noisy data, and instead of looking at a singular month of observations, we're able to use over 6 years of historical patrol data to learn much more smooth patterns about general levels of patrol effort and general levels of poaching risk. By building these machine learning models to create broader predictions of typical poaching patterns and typical patrol patterns, this enables us to make the inputs into our causal inference model much more reliable and much less sensitive to noise. And altogether, this approach enables us to provide the first evidence of causal evidence of deterrence in the context of ranger patrols. So what we find is that a typical site in Murchison Falls has about a 21% probability of poaching. And then when rangers patrol an additional kilometer during our field test, the probability of poaching in the subsequent month declined to about 12%. So that's about a 45% reduction in poaching probability, which we believe is very significant. And we're excited about this outcome because we believe that it could be used to help justify to potential funders or policymakers that indeed ranger patrols are important. We need more of it. And to just give you a sense of the scale of these efforts, globally, there are about 300,000 rangers, but Nature Sustainability article has estimated that the number of rangers we'll need in order to reach 30 by 30 is 1.5 million. So we really need like a 5x in the number of rangers. But in order to convince people that we need to pay money for another 1.2 million rangers, we need to be able to show that they're actually effective in the work that they do. Okay. So now we've looked at the general challenge of poaching prediction and patrol planning. We looked a little bit at online learning for the setting and causal inference, but to kind of bring these bits together. Challenges that we want to face when it comes to biodiversity and nature is we have some, abstract notion of the world. We want to plan an idealized intervention to get us to ideally some better state in the future. And the things we might care about could be things like the density of animals in an area or some notion of ecosystem status. And we want to plan an intervention that makes us all better with respect to some objective that we define. So just throw on some different terms here. We have, the current health of our ecosystem as the state. We want to determine an optimal action that brings us to a next state that helps us maximize reward. So many of you might recognize this general paradigm is that of a Markov decision process, because these types of environmental challenges are really dynamic, are really working in dynamic problem settings. We have to think about our action not just as something that's like static, but that's something that has to be made like iteratively and repeatedly in the face of a changing environment. We can throw in like a lot of tools here. So predictive supervised learning tools can help us understand the state of the world. So this is really where computer vision has made extreme advances for these sustainability challenges, because now we're able to monitor deforestation. We're able to like monitor animal presence at a much more global scale very cheaply. Causal inference can help us build these types of dynamic models. We really can isolate the impact of our action separated from exogenous changes, like just natural dynamics are happening in that system. And then reinforcement learning is really the subfield that's focused on how to effectively solve Markov decision processes effectively. But there's many challenges across all of these, all aspects of this process. And all of these challenges really kind of guide us towards which research directions are interesting and challenging for this problem setting. So I'll talk about some of my work on helping to address one of these challenges, which is uncertainty. So what we've seen based on the data from Murchison Falls National Park in Uganda is that there is deterrence in this context where when we patrol an area more, the probability of poaching goes down in the next month. So based on this model we just looked at, this tells us that we really need to be thinking about sequential planning. So to work on sequential planning, we might look towards reinforcement learning, but effective work in RL requires that we have a good model of the environment so that we can treat it as a simulator and then use that to learn an optimal policy. But even if we get some estimate of when we patrol this area more, poaching goes down by this amount, because our data is imperfect, we can't be too confident that this is like a very precise value. So instead, we might want to be able to relax that estimate into some interval. So if we instead say that this number falls between, let's say, 12 and 23%, then we will have much greater reliability. So this tells us that we need to do robust planning in the face of uncertainty. But RL is really kind of like generally a computationally intensive process, and introducing uncertainty really widens the space of what the state could be and what the transition dynamics that we have to look at when we take an action. So bringing in uncertainty really makes the computational approach to solving RL problems kind of exponentially harder. Especially because the way that we define robust planning in this context is with a new objective for RL, which is known as minimizing the maximum regret, which is basically for any value of what the true environment parameters could be within this uncertainty space. We want to make sure that the policy we end up choosing will perform reasonably well, regardless of what the true environment parameter values could be. So to make this hard objective more tractable, we formulate this problem as a two-player zero-sum game between like a planner who's trying to learn an optimal policy and an opponent, which is representing this level of uncertainty in the environment. And basically, we model an iterative process where we try to learn an optimal policy, and then our adversary tries to make the environment like as adversarial, as bad as possible for us with respect to the policy that we just picked. And then we repeat this process, which enables us to tractably search this very, very large planning space in a much more efficient way. And we prove that this approach converges to a policy that is within epsilon of the optimal action. So again, this work is just really to try to highlight that, you know, this all of this work can like use inspired machine learning when we're focused on the problem setting and focused on like what policies, what algorithms do we wish that we could apply in this context? What breaks? Why doesn't it work? And how can we, you know, help overcome this a little bit to make these types of generally effective decision-making tools more accessible for these kinds of messy, practical, real-world problems. Okay, so that's kind of the end of what I'll talk about when it comes to anything technical, and especially given, I think, the interest of many of you at OII, I also want to talk a little bit about ethics and participation more broadly. So probably all of you recognize this image. You know, it is like this ProPublica article from I think 2016, which really like you know, this features on like every single ML fairness talk, you know, for over the course of 5 years. Where we really saw that that predictive algorithms can be extremely biased when it comes to sensitive traits like race. So, you know, this is really kind of surfacing to the general public that there's a lot of bias, even in machine learning, and subsequent studies show that, you know, in part, the algorithms were biased because underlying data was biased. And unfortunately, that is the case as well when it comes to biodiversity data. So our knowledge of like where biodiversity is, like where valuable ecosystems and species are in the world, really is correlated very highly with income and also human presence. So we have a lot more observations of biodiversity in North America and Western Europe than we do in the rest of the world. But surprisingly, unsurprisingly, that is not in fact where the majority of the biodiversity is. So you'll notice that, for example, like the Amazon, which is among the most biodiverse regions in the world, has very few observations relative to Western countries. But because we're also at this moment where we have all this international attention being paid to biodiversity conservation, there's all this resources and attention that's being driven towards like, where should we allocate money? Like what types of actions and interventions should we be taking? And those decisions are really driven by the data, which is highly biased. So I was a co-author on this paper led by Millie Chapman, who is starting as faculty at ETH Zurich this fall, but she works in environmental science policy. And this is just like a policy forum piece that we wrote that's talking about some of the ethical challenges and the inequities embedded in biodiversity data. So one of the things that we discuss is that this data is biased not just in terms of income, where there's a lot more biodiversity data in high-income countries or high-income hectares regions in the world versus low and middle income regions. But that you can also see signs of historical segregation. So this is looking in the United States at urban areas that were historically redlined versus not redlined. And you see that there's many more observations of biodiversity in areas that were not redlined than those that were. You can see legacies of colonization. So looking at Nigeria, during the period where they were colonized by Great Britain, very significant, almost half the data that was collected was by Great Britain and kind of only a similar amount by Nigeria. But then post-independence, the amount of data that was kind of collected and owned by the former colonizer really shrunk. And then they were able to have kind of a lot more like data stewardship and data sovereignty. And you can also see legacies of conflict and warfare. So this is looking at Cambodia during the period of the Khmer Rouge. And during that period, there was a very significant drop in the availability and collection of biodiversity data. This, unfortunately, we don't have like really a solution, but this is just kind of like a warning that this is the best available data that's used to guide this very intensive like multilateral shifts in funding. So part of the Global Biodiversity Framework that was signed in 2022, is mobilizing an additional $200 billion per year of data, of money towards conservation efforts. It's a commitment to reducing $500 billion a year in harmful subsidies, and on top of increasing the amount of protected areas on land and water. So there's a lot that I think needs to be done very quickly to meet this moment, where there's both kind of like an increased sense of awareness, but also like the sense of the mobilization that is currently happening. Okay, and I have one last bit that I want to talk about, and this is comes from a paper that we published in ES in 2021, where the lab where I did my PhD under Professor Milan-Tambe, like we kind of referred to our general work as AI for Social Good, but I had a series of discussions with a few of my lab mates saying, like, has anybody really, have like a concrete guideline for like what is social good and what is not, and how do we decide what problems to work on? Because the AI part is pretty straightforward, but social good is like, what is it? And more importantly, who gets to decide whether or not a project counts as social good? And I think there's I don't know if there have been any that have happened really very recently, but for a period of like 5 or 6 years, there were all these like workshops and conferences of like AI for good at all of the big machine learning and data science conferences. So, it was really a question of when we were reviewing these papers, for example, like I was asked to review a paper that was creating more personalized recommendations for marathon runners. And this was a paper that was submitted to a social good workshop. And even though the paper was like fairly like well done, it seemed like they were actually like working with like an actual lab where people were enrolled and this like training plan. But my review said like, even though this work is good, I don't think that it should belong in a social good conference because I don't think that marathon runners are really the population that this work should be aimed towards. But this kind of like drove us on this little journey of trying to understand, can we find at least an answer for ourselves of what that should look like? And the approach that we pitch in our paper is a framework called PACT, which stands for Participatory Approach to Enable Capabilities in Communities. And the kind of high level concept is that it should be really the impacted communities and stakeholders and not AI researchers who get to define what social good means in their context. And the framework that we propose really draws on this capabilities approach, which comes from the developmental economics literature. So it was first proposed by Amartya Sen and Martha Nussbaum, with the goal of measuring human development, not by GDP, but rather on the substantive liberties that individuals and community members enjoy in order to lead the kind of lives that they have reason to value. And this capabilities approach was the foundation of the UN Human Development Index, which was then created and adopted in 1990. But what capabilities refers to are first, we have functionings, which are kind of like the end goal. So the functioning is something that you either be or do. So for example, like, you could be a student and you can like do learning, you can do research or something like that. And capabilities are the opportunities to achieve certain functionings. So one thing I really appreciate about the capabilities approaches is that it's not necessarily prescriptive in terms of like, okay, everybody should go to college, but rather it's offering capabilities to everyone should have the ability to go to college if they choose to do so. And what capabilities hope to enable is then the freedom and choice to then achieve well-being, however you define it. So kind of working backwards, the ultimate things are functionings, which are what you can either be or do. A set of capabilities enables you to achieve functionings that each individual can choose to enable. And therefore, we can think of this notion of improving human welfare as either expanding or equalizing to redistribute capability sets. And our argument for how and why AI can compare nicely with the capabilities approach is because AI really has the potential, both good and bad, to change human capabilities. So AI kind of increasingly more so now than when we wrote this paper in 2021, but AI can help foster internal characteristics. So AI can be used, to help like somebody learn or like build up new skills. AI can provide external resources. So any kind of like distributive like resource allocation tool, whether it's, like determination of like who gets to qualify for a loan, for example, if that's determined by an AI algorithm, that really changes people's capabilities. But AI also alters the wider material and social environment in which we operate. So, we could just think of like the world of social media and digitalization. We can think of community surveillance systems as really changing our broader social environment. So all of these things together then create capability sets, which then people can choose to achieve various functionings. And then what we argue for in our paper is then the process of determining these capability sets should really be driven by the community members through some sort of participatory approach. And then that enables you to kind of like work backwards. So then in trying to like design an AI for social good project, for example, like first start with trying to figure out like what change within people's existing capability sets do we want to either expand or equalize? And then what can we do either in the wider social environment or in terms of resource allocation or in terms of fostering individual skills, can we then help achieve through the development of AI, for example? Okay, so that's pretty much what I had for you, and I just wanted to kind of like zoom out on my research more broadly. So my work really focuses on effective decision making in the face of uncertainty for real world challenges with a big focus on conservation. So really starts with the data and then developing learning algorithms that tries to make better use of limited data so that we can converge faster and be more sample efficient. Then taking the models that we've built to do planning, including with reinforcement learning and optimization, trying to evaluate the impact of our actions using causal inference, and then also working with partners to help scale up the actual deployment of these systems. And then the broad question I would say that guides my research is how can we make better decisions in high stakes settings with messy, incomplete data for planetary health challenges? One thing that I really had the privilege of experiencing throughout my PhD through a very supportive advisor is being able to be closely immersed in the problems that I'm working with. So I had the opportunity to do field visits to Cambodia, Belize, and Uganda, where I got to meet with park rangers, go on patrol, and help really understand like the context in which they're making decisions and the constraints that they face. I'm happy to come back to this about just kind of some other questions I'd be excited to explore, but I'll just close off by thanking my collaborators. Thank you so much.
Let me just check if okay, we can start with questions in the room. Yeah.
Hello.
I'm curious, this is something that you may not know about, but what do the poachers know?
Yeah.
I mean, you know, there are all these rangers out there, and what do we know about poachers' behavior or thinking? Because, you know, I can imagine a kind of technological war taking place. You know, they know that you're kind of optimizing the algorithms for the rangers, so they might put a sensor onto their snares so that they can deploy a system whereby they can move the snares wherever you guys aren't looking for them. I'm sorry to spin out such a sci-fi, but do we know what they know, or is this a black box? Or
So I would say that there's tons of variation. In Cambodia and Uganda, for example, where I have worked, we tend to be in like more like resource scarce, like low technology settings. But there are certainly other parks where both sides have a lot more sophistication. So rangers are using drones, and poachers are using like special like satellite communication devices and stuff like that. But generally, for example, the specific question that you asked, like if there was some kind of tracker or sensor on these snares, like rangers would see it because it's it's like a small piece of wire, and you would see if there's some kind of like electronic gadget on it. But generally, because these landscapes are so large, like you can imagine like operating something like the size of a forest, but the size of a large forest. The presence of both rangers and poachers at the same time is very unlikely. So like they actually very rarely encounter each other directly, which is why snare removal is really the way that rangers kind of like make their actions more visible. Just to give you an example of how like that kind of understanding of what poachers know kind of guided our research is because some past work of trying to do like patrol planning really focused on building like strong game theoretic models where we were thinking of like perfect information settings where the poachers are best responding to our actions. So they're observing what we're doing and then, or observing the kind of like general like approach, some kind of randomized schedule, for example, that will be doing patrols and then best responding accordingly. But that assumption means that poachers will know exactly where rangers are. But because rangers, which are much more sophisticated and much more coordinated, don't even know what poachers are doing, like that assumption of full information and a perfect rationality really falls apart. And furthermore, poaching is extremely distributed. So it's really a lot of, hundreds, if not thousands of like individual people or groups going out and placing snares. And for the most part, they're not communicating with each other. So this game theoretic assumption of there being a centralized decision maker on the side of the adversary who's kind of like colluding and sharing information and planning all together is not really a reasonable assumption in this problem setting. Yes.
Thank you for the talk, super interesting. I had a question about learning about the data that you get from the rangers, from those working on the field, and how that the step of translating that into data that's ingestible for your model. I was wondering if it has the dependence on specific like geospatial or temporal resolutions, and if that's the case, kind of how do you deal with that in terms of trying to then go outside of your specific geospatial context into other parks, for example? And have you maybe noticed that this is created as like a positive externality, a sort of template that park rangers can use to actually improve their data reporting to make it easier for models like yours to work?
Yeah, no, that's an awesome question. And we had tried to look at transfer learning where we like build one model on like park that had like a lot of data and then applying that to other contexts. And basically what we found is that every time we tried to apply transfer learning, even when it was two parks within the same country, for example, it actually was worse than if we just started with like a blank model. Because there are, and that really highlights to us that there's so many like there's so much difference in the specific like local context of each problem setting. So first, like the animals, the species present are different. Like the income and like the habits and like the values of that local community of what is desirable to be consumed also varies drastically. And just there's differences when it comes to like landscape and everything. So we weren't able to like build models that transferred effectively. We were really looking at this maybe like 3 or 4 years ago, and I know that there's been significant work done in the field of transfer learning since then. So perhaps there are more opportunities to do so. But in another context, another challenge here is really much more like political and bureaucratic. So oftentimes this data is government data that's like very highly classified. It's like owned by the government. And sometimes they don't even want it like leaving their country's borders. So they won't use cloud computing, for example. They're only hosted on their country servers. So the possibility of like sharing data across multiple groups does it it's not possible for the most part for us to like build generalized models because people don't want to be sharing data, even if it's in this kind of like abstract indirect form of a pre-trained model. Yep.
So yeah, also thank you for the talk that touched on very many interesting areas. I have a question regarding the kind of ethics aspect with this. Like you point out, there's this kind of these inequities in where data is collected.
Yeah.
And I was wondering whether it would be possible, similarly to how you did in the kind of park modeling, to use some machine learning methods to kind of more equitably infer data and to maybe like create a better, or whether you think that would create a better kind of foundation for making decisions than what exists now.
Yeah, so I'm very interested in these questions of like, can we use like optimization approaches to inform data collection? So aside from the online learning work that I described, like the decision of like where to place sensors, for example, and how do we figure out like the process that we should be like moving sensors around or whatnot. So oftentimes the sensors used in these contexts are bioacoustic monitoring, so like audio recordings of both wildlife and potentially you can hear things like a chainsaw. with bioacoustics, but then also like camera traps, which are meant to try to like estimate like biodiversity presence and richness in a certain area. And actually, I know somebody who is working on like an environmental nonprofit called Gain Forest. And his some of you might be familiar with him. His name is David Dow. He worked a lot on like Shapley values as a machine learning researcher, but he has founded a nonprofit called Gain Forest, which works in the Brazilian Amazon by paying community members for the audio data that they're recording. So basically, like he'll give payment like per minute of data that they collect. So I find that work really fascinating. And one idea that I've like always had that I have yet to pitch to David is thinking about like additional incentive mechanisms to encourage community members to like place more sensors in areas, you know, where we either have like a lot of uncertainty or we think that there might be like significant like biodiversity value, for example. But that would, you know, really be at this intersection of like active learning and also like equity challenges, because, you know, thinking of who has access to go to a certain area, who, you know, what is like somebody's like willingness to pay to, or willingness to accept a certain amount of payment for the amount of data that's being collected. So I think those notions of like, how do we trade off between equitable payments to everyone versus, you know, potentially paying some people more for data that's like more worthwhile or more valuable, for example. I think those are really interesting directions to go into.
We have a technical question online that says, won't all the snares be set along animal paths? Could it be possible to use a drone to identify likely snare locations by detecting animal paths rather than the snares themselves, and then reduce the search space?
Yeah, that's a good question. Thank you, Adrian. So yes, oftentimes snares are set very strategically, so they're placed kind of like on like along an animal trail or like on the way to like a water source, for example. And poachers are actually very strategic. Like sometimes if it's like a woody covered area, they'll actually like forge a new trail on the way to like a water source and place a snare there, because that kind of funnels animals in. But the challenge is that, you know, there's just so many of them. Like there's not like you know, many of these sites, the one in Cambodia, for example, is really a savanna, and that means that you know, you can walk between. Oftentimes, you can even like drive between many of the trees. So it's not very concentrated trails like you would have for like human roads, for example. Like it's really this very complex, very dense network all throughout. That is a good idea. Yes.
Thanks for the talk. Did you find it hard to like motivate buy-in for machine learning with the like rangers? And do you have any tips for that?
Yeah. So definitely, like one of the things that we that helped us is because we were working with SMART, which works with many different parks. There are some parks that we talked to who are just kind of like, you know, we don't have capacity to like use or try anything else, we're not interested. But there were others who are really excited about, like, you know, we are keen to you know, have more informed decision making and have better insight from our data. So I think this is really like a reminder that, you know, as researchers, when we're working with community partners, we want to make things as frictionless as possible. So finding ways to like not ask them to collect new data, like not really change their methods, like understanding like what tools they're using, what processes they're currently working with, and figuring out like how can we fit into that as smoothly as possible. So for example, like when I was working in Cambodia, like I learned that their patrol planning happens in terms of like monthly meetings, and they meet on the 11th of every month. So I'm like, okay, like let's have a meeting like with me and like the manager on the 4th of the month so that we can kind of like, you know, give you these recommendations, and then you'll have like a week to plan it out, you know, if you want to like make printouts or anything like that. So really just trying to like schedule ourselves in and like provide like resources and do information sharing in a way that kind of, you know, adapts most nicely with the infrastructure and the processes that we have. Yeah.
Yeah, thank you so much for the talk. It was super interesting. I was wondering if you could provide a bit more information on the ensemble model that you constructed to make the predictions for the routes.
Yeah, so the ensemble model that we used was really like the biggest challenge we had there was class imbalance. And again, you know, I I feel like I'm kind of giving away all my tricks, which is just a single trick, which is again this notion that the areas where we have more patrol effort are more reliable. So our ensemble like, creates different buckets of the data depending on like how much patrol effort was exerted, and you know all the negative instances in with the highest amount of patrol effort are weighed more strongly than buckets of data with like lower levels of patrol effort.
Yeah, okay, thank you.
Yeah, but then the way that we like weighted this ensemble like came in the cross-validation period. So we basically like create this ensembling and then with all these buckets based on patrol effort, and then we like learned the weights of this with cross-validation.
Okay, we're almost at time. I think well, let's thank the speaker and